and warmly welcome to today's seminar to be held by Andreas Kirchning on the topic of On the Usefulness of Useless Knowledge, or How Free is Science Today? Andreas is a sabbatical fellow here at SCAS and also a professor of chemistry at Leibniz University, Hanover, and also a guest professor of chemistry at the Uppsala Biomedical Center, or BMC, here at Uppsala University. He received his doctorate in chemistry from the University of Hamburg in 1989, and then he had a postdoctoral fellowship at the University of Washington from 89 to 90, after which he habilitated at the Technische Universität Clausthal in 1996. And in the year of 2000, he became full professor at Leibniz University, Hanover. I would like to say, reading his CV and his application or nomination to the fellowship here, that the international component of his research trajectory is clearly articulated, as you can see also from where he has been. And so is his curiosity towards other disciplines, and I believe this will become evident in today's talk as well. He's been a visiting professor at various universities, including Madison, Rennes, Le Mans, Strasbourg, Rome in Italy, and at Indian Institute of Technology, Indore in India. Since 2024, he has been affiliated with the department I mentioned at Uppsala University as a guest professor, and he will be the Tage Erlander Professor funded by the Swedish Research Council here in Uppsala next year. He's also had a number of institutional responsibilities, and among them I'd like to mention that he was Vice Dean at the Faculty of Natural Science of Leibniz University, Hanover. He's been head of the Institute of Organic Chemistry, also at the same university, and coordinator of internationalization in chemistry and life sciences. And he's been a member of the Royal Society of Chemistry. His research is located in the field of natural product chemistry, with a particular focus on the search for new anti-infectives and anti-tumor active substances. In this context, his group, I'm proud to say, pioneered the introduction of flow chemistry, an enabling technology already around 25 years ago. In more recent years, and as a result, he says, of attending seminars in philosophy, he got interested in explorations on the origins of life and the question of chemical evolution, which must have preceded the biological evolution of life. And since then, he has published several papers, some of them in collaboration with philosophers. Some of the papers, journals he has published in are Natural Products Reports, Angewandte Chemie International Edition, and Chemistry. And here at SCAS, he continues, I believe, his theoretical work on chemical evolution, focusing on the role of certain metals during the transition from abiotic to biotic evolution, in collaboration with the Department of Earth Sciences here at the Uppsala University. But I believe he will talk more broadly today on a topic well known to us, so warmly welcome, Andreas.
Christina, thank you very much for the long introduction, much too long introduction. There's not that much to say, really. For me, this is an unusual situation. Not that I'm a scholar here at this institution, but having experienced the last two talks, and I have to particularly thank you, Anders. I really enjoyed that one because it had this link between, I'd say, historical sciences and natural sciences. I feel really a little bit under pressure whether I can fulfill any expectations you might have to me. Because in some ways I've learned that I'm a little bit exotic here because I would call it a natural scientist. I just learned from you yesterday that scientists in the English language is a little bit more focused on, let's say, the experimental probably fields, In Germany we have the word, and in Sweden as well, Wissenschaft or Vetenskap, and everybody under fulfilling the rules, let's say, going back to Francis Bacon, is ein Wissenschaftler or Wissenschaftlerin. So in that respect, we are one family. But again, I come from a slightly different background than most of you. What is also different for me under these circumstances, usually when we present presentations and provide seminars, we don't have a text. We usually have lots of overheads or PowerPoint presentation, and we run along those lines of structures and mechanisms and what have you. Today, I have to manage somehow that you get the feeling that I'm addressing you, but at the same time I'm reading. I apologize if you don't feel, let's say, feel that there is enough contact during my talk between the two, between you and me. Okay, so what can we expect in the next 45 minutes or so? It will be probably a passionate plea for fundamental research, or something like Leibniz meets Humboldt. We will hear about Humboldt at the end, indirectly, but we will hear about Leibniz as well. And when you look at the top left little logo, this is the logo of Leibniz University, and it has to do with Leibniz, although the university has nothing to do really with Leibniz in time because it was founded much later. But we will come to that, these figures over there, or numbers. I will talk, there will be quite a lot of biological stuff in there, especially nucleic acids. If you don't understand all what I'm going to talk about, the underlying message will be more the historical development from fundamental research to applied science. And the steps in between and the description of the individual steps, I hope will be understood to some degree, but if not, the overall message, especially at the end, will be probably also a little bit provocative. So let us start. So first of all, what you mentioned in your introduction, I have prepared to some degree. I didn't know that you would go in such a depth into our research. So it's difficult really to pinpoint one kind of research topic, but overall, over the years, it's about new antibiotics and antivirals from natural sources. And I could equally, now as I realize what the atmosphere here is, have given a talk on the antibiotic dilemma. And this is not only about developing the antibiotics or the history, but it's really about the current situation of why do we need antibiotics, and at the same time is no fundamental research in an industrial environment being conducted. There is a discrepancy. But I will not talk about this. Just to give you a flavor, we have been involved in collaborative work with biochemists and pharmacologists and microbiologists, people from botany all over the world, in order to extract new natural products, which then are further developed to become probably a drug. In particular, the top one from this tree, Indonesian tree, the structure doesn't matter, is a compound that has broad antiviral activities, especially also, as was found out in recent years in our collaboration against coronaviruses. But it's still an intellectual and fundamental research in order to get to that far to the point of a drug. And the same applies to the other structure that comes from a myxobacteria, bacterial source, which is a new broadband antibiotic, but has over 10, 12 years huge problems in a large consortium to get it really to preclinical studies. Anyway, this would be a different story. But let us start now with the Institute of Advanced Study, not in Uppsala, but in Princeton. Many breakthroughs in research are not plannable and cannot be planned. And it is not common for the passion of individuals to produce great insights and spur discoveries. Abraham Flexner, the founding Secretary General of the Institute of Advanced Study at Princeton, an independent center for theoretical research and intellectual inquiry, founded in 1930, by the way, Albert Einstein's last place of work, wrote an essay on basic research in November 1939, which he entitled The Usefulness of Useless Knowledge. So this is not the title invented by me, it is the direct link, and it has to do with SCAS, why I've chosen it. There, Flexner described how seemingly random experiments driven by curiosity eventually lead to significant findings. He argued vehemently against the need for utility in the promotion of research and the allocation of funds. The article is an eloquent discourse on the utility and virtues of freedom and basic research, much in line with Flexner's guiding principle when founding the Institute, namely to be committed to the pursuit of knowledge for its own sake. Knowledge emerges when intellectual pursuit is freed from the constraints of concrete applications and narrowly set goals. Quote, knowledge must come before application, wrote Max Planck, and this has remained the guiding principle of the Max Planck Society up to today. The focus on basic research, the uncompromising pursuit of excellence, and the recruitment of the very best make the Max Planck Society one of the most renowned research institutions in the world. No fewer than 31 Nobel Prize winners have emerged from the ranks of the Society since 1948. 3 over the past 3 years alone. Ultimately, curiosity-driven research is the engine that leads to innovation. The road there is long and winding. Shortcuts are rarely in sight. Basic research is time-consuming and expensive, and it is increasingly difficult to explain this meaningfulness to the public, legislators and decision makers and ministries and business. This is because today's prevailing policy looks at the value of research with an eye of usefulness. Whether the research goal addresses a social problem or whether it is possible to deliver a marketable product in the foreseeable future, preferably within a few years. I mean, I'm aware of that. This is, of course, a view that is very linked to natural sciences, but I mean it really general. Yeah, for all of us, basically. But before I delve further into this issue, allow me to first examine the topic in more detail using 3 examples. Current ones, and one rather historical, one right at the beginning, which is closely related to the region where my home university is situated. So first 3 lengthy examples, and then we will come to a more, let's say, probably political conclusion. Since the middle of the last century, pioneered by Konrad Zuse and Johann von Neumann, but also by others, we have witnessed the emergence of electronic calculating machines, precursors for our digital world and hence of the contemporary digital tsunami AI. This world is represented in a binary number system, and this system in which the first all numbers and nowadays all information is expressed with the signs 0 and 1. Or in a broader sense with true and false. It has turned our lives, our societies, and the economy upside down in every respect. So, who would want to question the meaningfulness of the digital world with a binary code as its basis? It's a bit of the history, but almost 330 years ago, in the run-up to the Enlightenment, more precisely in 1697, Gottfried Wilhelm Leibniz explained the binary number system in a New Year's letter to Duke Anton Ulrich von Wolfenbüttel, which is based on traditional philosophical thought and describes the one as the unit or the only one, while the zero or nullum describes nothingness or the lack of existence. In this sense, the binary number system, in which all numbers are built from 0 and 1, and probably I will briefly go back. I think now the logo makes sense. It's the original scribbling from his papers. The binary number system, in which all numbers are built from 0 and 1, could be understood as a symbol of divine creation. In the context of his first publication for the Académie des Sciences in Paris, Leibniz addressed the binary number system and pointed out that the binary system was not suitable for use in everyday life. But for scientific purposes, as structures were easier to recognize and grasp. The Academy's interest in the subject, as Academy documents reveal, was limited. The Englishman George Boole developed Boolean algebra on the basis of the binary system about 1.5 centuries after Leibniz, another milestone on the way to the emergence of modern computer science, and finally the first personal computer in 1974. This algebra generalizes the properties of the logical operators and, or, and not, and forms the basis of digital electronics in the form of so-called Boolean algebra. It is used today in all modern programming languages. So how meaningful was this Leibnizian mind game for people in the transition from the Renaissance to the epoch of Enlightenment, when even educated members of the Academy rather shrugged at the publication? I'm just imagining Hanover in those days. You go on the marketplace, you see the market people selling their fruits or their vegetables, and you tell them, use 1 and 0. It would have been absolutely useless. Yeah? It should be noted that independent of these European mind games in the field of binary arithmetic, signs are found based on a binary code in the I Ching, a Chinese text from the 3rd millennium BC, and there the reference to the duality of yin and yang is found. But let's turn to a more current topic, one that this time doesn't catapult us centuries back into the past to the early Enlightenment. In 2020, Emmanuelle Charpentier received the Nobel Prize in Chemistry together with her colleague Jennifer Doudna from Berkeley. CRISPR-Cas systems, such as CRISPR-Cas9, is an adaptive immune response concept that protects prokaryotes, which are bacteria, for example, from bacteriophages, which are viruses that are specifically addressing bacteria and not human cells. These molecular scissors cleave the nucleic acid of invading viruses and thus protect prokaryotes from viral infections. But before we continue, let's briefly look at nucleic acids. They will come again, and I don't know how familiar it is a very well established biomolecular polymers, but I will a little bit or give you background on DNA and RNA. Desoxynucleic acid and ribonucleic acid are the most important representatives to mention here. They are molecular data carriers or information carriers, with information packets organized in genes. RNA also serves as a translator of this information into hardware. In a biological sense, proteins, on everyday language, the egg, the daily morning egg, can be described as hardware. This is because they are tangible and plastic for us, like a boiled egg. Nucleic acids, especially RNAs, act similarly to a computer program that guides and directs robots so that a vehicle, which is the hardware, is ultimately produced on an assembly line. We will encounter nucleic acid frequently throughout this presentation, but now back to the gene editing tool. The use of CRISPR-Cas9 to edit genes came into the spotlight in 2012, 8 years before it was honored with the Nobel Prize, and generated widespread attention when George Church, Jennifer Doudna, Emmanuel Charpentier, and Feng Chang first used it as a tool to alter targeted regions of genomes. A tool. It's not knowledge, now it has become a tool. CRISPR-Cas thus works like a cut-and-paste tool to alter genomes by engineering a guide RNA to target a specific region in the genome. As a DNA editing tool, CRISPR-Cas can remove genes, so information, off or activate them. The potential of this technology for biotechnology and biomedical research, especially for hereditary diseases such as cystic fibrosis or sickle cell anemia, but also for cancer and infectious diseases, and finally for new agricultural technologies, is still hard to grasp. This is because in recent years the Cas system has also been extended to epigenome editing. The market for CRISPR technology is estimated at $2 billion in 2021, and the sales forecast for 28 is currently above $7.5 billion. In fact, the beginning of basic research on CRISPRs, these repetitive DNA sequences in bacteria, can be dated to the year 1987. When the team led by Japanese scientist Yoshizumi Ishino first discovered them in Escherichia coli. However, at that time, the function of these arrays remained a mystery. It was just a description and collection of data and knowledge. In 1993, researchers led by G.D. van Emden in the Netherlands discovered that different strains of Mycobacterium tuberculosis, which is the tuberculosis pathogen, contain different spacer sequences between repeats. So there were additional elements in the DNA. They found them. They were everywhere, but they couldn't make sense of it. Subsequently, these sequences were also identified in several other bacterial genomes, so it was a very general observation. Later, researchers, Francisca Mojica and Ruth Janssen, were then the first to call these elements CRISPRs, clustered, regularly interspaced, short palindromic repeats. At the beginning of the 2000s, the same research group then discovered that the spacer sequences, so these new unknown elements, resemble sequences that also occur in viruses. And suddenly there was a link between, okay, viruses have them also, bacteria, what's the link? What's the reason for that? And especially in those that are called bacteriophages, which these are viruses that specifically choose bacteria as host cells, as well as plasmids. This means that these DNA sequences occur homologously in cells as well as in viruses, a very unusual finding. However, they also found that viruses cannot infect bacteria when they carry homologous spatial sequences. So it suggested that these sequences play a role in the adaptive immune system of microorganisms or prokaryotes. So the period from 1987 till 2012, a journey into the unknown, belonged to basic research alone. For a quarter of a century, research on CRISPRs was focused purely on gaining knowledge. And only then did the field open up in the direction of technology. Let me come to the third example, and this will be a bit longer before I will give a more general overview on what this might mean for today. Let's consider another example, highly topical, a hope for the world now and in the future, a single joy for markets and stock exchanges, and a blessing for mankind. Indeed, the mRNA vaccine and drug concept finally left the ivory tower in 2019, not 2020. We all remember the race for the ultimate vaccine when the pandemic had just started. BioNTech, a biotech company, exemplary for other biotech companies, was able to report breathtaking development and translational achievements in a short time under the time pressure of the pandemic situation. The big pharmaceutical companies, according to Pfizer, acted as steerer partners for approval, production, and distribution. They had the power to rapidly produce and distribute these new vaccines. They were not developed by them. Just one headline of many on mRNA technology from the Süddeutsche Zeitung, the respected daily newspaper in Germany, from the 21st of November 1921, Eiffel Tower, moon landing, mRNA. So that says a lot how this new technology hit even, let's say, general public. The turnover that the companies BioNTech and Moderna achieved with the two vaccines is estimated at more than $50 billion for 2021 alone. I don't know what the latest figures are. So what is the basis for using mRNA or messenger RNA as a vaccine or therapy concept? This is a very, very long journey. And most of the time it was fundamental research accumulating knowledge. Here, mRNA serves a kind of software or blueprint for proteins. Such as the spike protein found in the outer shell of coronaviruses. So the coronavirus has sort of information, and it is sort of encased in a protein. Yeah? So it's basically a container based on protein. This blueprint can code for the production of key proteins, such as the spike protein found in the outer shell of coronaviruses. So the information inside is the information to make the shell for the new viruses. Our immune system responds to the protein, not to the RNA or the information. It only sees the outer surface of the protein of the viruses and tries to attack it. The problem, of course, is if the virus multiplies very quickly, the body is deaf before the immune system has found a suitable tool to target the protein, because it has to be trained on what it sees as being not me. If I am not fully correct, please correct me, Peter. You are the expert. I'm just a chemist. The immune response or defense mechanism is initiated by our body, even though this protein is not part of a complete virus. So once we get the information, we can produce the protein. And that's what the virus makes use of it. So our body itself serves as a production site, and the mRNA vaccine delivers this blueprint to our cells. Its production is initiated, and subsequently the viral but non-pathogenic spike protein is presented to our immune system. In this context, I switch now. The public became acquainted with two remarkable personalities who represent the company BioNTech. Where are they? They were here. Ugur Sahin, a medical doctor, and Özlem Türeci, a molecular physician, both habilitated in Düsseldorf, stand for the success of the technology in Germany and beyond, at least in the public eye, and it is raining prizes. But these list a 30-year name, usually when these prizes were given, and we will see, and that's the Hungarian-American biochemist Katalin Karikó. Until 2022, vice president at BioNTech, and I would delve into her life a little bit. Her curriculum vitae seems worth exploring in the light of the topic under discussion. I start with her immigration from Hungary to Philadelphia, USA in 1985, when she accepted an offer of a scientific position at Temple University. Beginning in 1990, mRNA therapy grant applications were consistently rejected. Basically, she had no research. She had no basis for research. Researching with minimal funds and resources, no luck in attracting external funding, her situation worsened in 1995 when the university gave her a choice. Either she leaves the university or she will take a demotion, including a pay cut. She decided to stay and continue her work under precarious conditions now as a postdoctoral researcher. In 1997, she moved into the laboratory of molecular biologist Drew Weissman at the University of Pennsylvania, where research on mRNA continued. Injections of laboratory-generated synthetic mRNA triggered massive inflammatory responses in mice. So RNA is not good as a vaccine in that respect. It became clear that the mRNA activates a series of immune sensors which react as the first line of defense, so to speak, to danger signals from pathogens. Their further research therefore focused on chemical changes in the mRNA building blocks. Yeah, they're made of 4 letters, and she was looking for probably changing a letter. The replacement of, and the letters are the information, the replacement of the nucleobase uracil by pseudouracil in the corresponding nucleotide monomers led to the breakthrough. How can I explain this? To explain it with link to us all here today, I would say we exchange the letter A in SCAS by an ä with 2 dots. Yeah? SCAS. So it would say Swedish Collegium of Advanced Study. I think we perfectly understand, but the immune system does not. So the inflammatory response didn't occur to the same extent, although the biological system, the replication system, still understood. Yeah, so just going from A to R to A in German, or R in Swedish. Unfortunately, the English has not taken up A and with 2 dots. However, it took until 2005 before the new findings were confirmed to be so solid that they were published. So for about 10 years or 8 years, no publication. 8 years after the laboratory change. Independently of this, and still not a matter of course in basic research, Karikó and Weissman applied for a patent for the scientific breakthrough. For the purpose of quick monetization, the University of Pennsylvania soon decided to grant an exclusive license of the patent to the lab supplier, a laboratory supplier. So they sell equipment, CellScript in Madison, Wisconsin, for a sum of $300,000. Later, as we know now, this small company would receive hundreds of millions of dollars in licensing fees from Moderna and BioNTech. The Tübingen-based company CureVac, the first biotech player in the business, on the other hand, pursued its own strategy to mitigate the body's immune response to mRNA by adapting a more classical approach, not being dependent of these licenses, or paying licenses. As we know, not a commercial success to date. Despite the breakthrough, another fundamental hurdle built up. The question arose of how mRNA could be protected at the same time. So we have to encase it now in order to bring it into the body. And at the same time enter the cell to start the production of the spike protein, in the case of SARS-CoV-2. Robert Langer, who had been researching mRNA for a long time, pointed out as early as 1976 that nucleic acids such as DNA and RNA are enveloped by proteins, and that a synthetic envelope, an artificial one, could be developed analogously to serve as a transport vessel, from which nucleic acids should be able to be released without causing any inflammatory reaction in the body. He received a lot of criticism for these thoughts. Many years later, in 2010, Langer became co-founder of the company Moderna, the packaging of current mRNA vaccines, which are lipid nanoparticles, are based on 4 different components whereby the latest developments just took place in recent years. Back to Katalin Karikó. Her academic career ended with the University of Pennsylvania not renewing her position. Her work, quote, does not meet the quality of the faculty. Presumably, publication performances, not enough, and no research funds or hardly any research funds. So basically, she failed in the academic system. As a result, she moved to the post of Senior Vice President of BioNTech in Mainz in 2013, and her name came up when future Nobel honors were discussed. And indeed, in 2023, Karikó and Weissman were honored with a Nobel Prize for Physiology and Medicine. She was the one with A and A, yeah? But if you want to know more about the history of mRNA vaccines, you have to look further into the past and find giants in biochemistry who made even more fundamental discoveries. Now we will go back to the beginning 1961. Such as Brenner, Monod, Jacobs, and Watson. In 1961, they described the isolation of messenger RNA for the first time and discussed the theoretical context that assigned it the role in gene regulation. Another prerequisite was the fundamental ability to produce biologically active mRNA in a targeted manner. At the time, both scientists pointed out that synthetic mRNA should mainly be regarded as a research tool for investigating gene functions. So we are here really on the left-hand side, and there was no idea that it would ever become of practical use. Only in the 90s with Katalin Karikó and others, it became clear probably there's a chance. Another early milestone in the convoluted history of MNR drugs is the 1987 experiment at Salz Institute for Biological Studies in La Jolla, California, in which these strands of RNA were mixed with fat droplets, so embedded in fat droplets, and this cocktail was taken up by human cells, which began to produce these proteins. Oops. So this was the beginning of that one could RNA treat as a drug. As early as 1978, scientists had used fatty membrane structures called liposomes, first described in 1965 by Alec Bangham in Cambridge, UK, to transport mRNA into cells of mice and humans and induce protein expression. So there were 2 lines. At the beginning, you had to learn about mRNA, and then you had to find the liposomes where you can embed them and package them. For a long time, mRNA was considered to be unstable, too expensive to be used as a drug or vaccine. Too expensive to be used. The path to mRNA vaccines is the result of the work of thousands of scientists over a period of more than 30 years, mostly localized in universities and research institutes, paid by taxpayers, more or less. So who deserves the success? the companies or the scientists who had laid the foundations. This was what Katalin Kariko was asked, and she, in her humble way, said, everyone simply did their part, including me. Looking back, many are simply pleased that mRNA vaccines are helping humanity today, and that they may have made a valuable contribution along the way. A curiosity-driven exercise par excellence, and that is before mRNA, enabled James Watson and Francis Crick to elucidate the structure of DNA double helix using cardboard models. A discovery that revolutionized the life sciences as a whole and must be seen as a starting point for the CRISPR system and mRNA agents, as explained here. The cardboard model was not the beginning. This manifested itself earlier with a new subdiscipline of biochemistry, but it was probably the greatest milestone on biology's way to becoming a molecular science. Consider Michael Faraday's groundbreaking work on electricity and the mysterious magnetism. Without his scientific interest in electromagnetism, which was considered an amusing but largely useless pastime in the first half of the 19th century, we would all still be in the dark. Faraday replied coolly to the then British Prime Minister William Gladstone when asked if his publicly funded research into electricity would ever be of any use. One day, sir, you may tax it. Gladstone did not live to see the rise of the electrical industry or benefit from the resulting tax revenues, but it should be noted that investments in useless research can pay off and be enormous in the long run. For example, although Albert Einstein's difficult to understand, almost esoteric general theory of relativity is seemingly irrelevant to practical applications, without it, there would be no GPS devices today. It was the seemingly random experiments that led to Röntgen's discovery of X-rays. Remarkably, the first lasers were described as, and that's what the physicists said in the 50s, why they developed lasers, in order to find a solution in search of a problem. That sounds quite funny today, I would say. Similarly, Paul Dirac's 1927 prediction of antimatter, which includes the positron, was considered at the time to be a completely useless curiosity with little, if any, practical significance. Decades later, positron emission tomographs are part of the equipment of larger hospitals, for example, for the early detection of cancer. The list is indeed endless. So there's no doubt basic research is a public good. It is almost entirely financed by taxes worldwide. It should remain an essentially public matter and must not be subjected to purely economic rules or politically opportunistic considerations. But for administrative institutions and, of course, for the stock exchanges, basic research reveals itself to be all too difficult to grasp and plan. It should be contained and success should be made measurable in digitalized form. Through so-called deliveries, we all know about that, milestones, and work packages. Unfortunately, a global trend that, thanks to the binary code, is taking hold of all areas of life. In his recent published History of Ideas, entitled World Without Measure, Ralph Konersmann, a cultural philosopher from the University of Kiel, points out that the two concepts of measure and measurement, or ethics and technology, morality and knowledge, are two sides of the same coin, and how this relationship is leading to a rupture due to the ubiquitous advance of measuring, counting, and calculating. Konersmann puts today's ubiquitous advance of measuring, counting, and calculating into a genealogical perspective through which we can only really understand it and better comprehend our present. He points out, for example, that we ourselves think we can validate the unmeasurable by comparison. Let's take the term beauty. Is it measurable? Can it be expressed in numbers? Beauty? Yes. If we replace it with another term, namely attractiveness. But this changes the meaning of the term beauty, doesn't it? Measured values and target agreements can be found everywhere in the science system today. Third-party funding, publications, or registered patents are counted. Ministries distribute money on the basis of such indicators, but these indicators are also becoming increasingly important in funding organizations like the German Research Council, as well as in university presidencies. Key figures are used to evaluate publications, scientists, faculties, and universities. Key figures decide on careers. In the meantime, the performance-based catalog of criteria has become even more differentiated. Not all third-party funding is the same. In Germany, it is the case if you acquire money through collaborative research centers, like SFBs, or from the European Research Council, these funds are ranked by university administrations and politicians as more valuable than those from the German Research Council, for example, for individual proposals, which we still have. €1 is therefore not €1. It's not equal to €1. It depends where it comes from. It looks a bit like a variant of Einstein's theory of relativity. And these research clusters of excellence in Germany that are rated as more valuable tend to camouflage mediocrity of individual parts. You have a large topic, 30 groups are embedded, and it's the easiest way if you are not sort of very strong to squeeze in and to get money. I mean, of course it is important, these huge centers, but it's not every part of these is excellent, really, but the label is there. Scientific journals have a journal impact factor, which expresses their reputation. Many publications look good on a CV, but many publications in high-ranking journals are many times better. In order to control the development of their impact factor, scientific publishers implement filters that allow only those manuscripts to pass through for peer review that are expected to strengthen the impact and ultimately, understandably, the economic success of the editor. This is done by means of a kind of upstream check by an AI. The critical and controversial dialogue essential for science is thus disturbed between scientists and evaluating each other because there is another filter put in between. The first description of CRISPR sequences that I mentioned appeared in the Journal of Bacteriology in 1987, a journal which in recent years has had an uninspiring impact factor of 3.1. These were just unspectacular results in the sense of this paper, useless knowledge. Publishers look for the most highly citable, preferably within 2 years of publication. And these are now topics that have already become fashionable. Look at the large number of mediocre publications on mRNA, besides very good ones, and SARS-CoV-2 that have appeared in high-impact journals since 2000 or around 2020. Or what was the impact of Leibniz publication submitted to the Académie des Sciences? Null. Yeah. One must criticize the outsized role of statistical key figures and rankings in research practice because they influence the freedom of science. Because these numbers often set undesirable incentives, especially fatal, and this is very important, I feel, for young researchers. They are stuck in a corset of formal measurements. In university appointment procedures, it is increasingly only about publication, third-party funding. Teaching is an accessory. So it's better to choose research topics that promise high third-party funding, and quick attention through citations. In other words, not too exotic and not too risky. Helmut Schwarz, president of the Alexander von Humboldt Foundation, from the year 2008 until 2017, is particularly concerned about young researchers when he writes, young researchers need freedom to pursue their thirst for knowledge and to test themselves and their ideas. Too much control and too many of them, many restrictions are fatal. For young people in particular, are full of enthusiasm, a passion that can develop into a genuine love of research, including basic research. These young talents need to be nurtured in a creative environment, judging them and their potential solely on the basis of bibliometric data or the amount of research funds raised is nonsensical, because such numerical indicators do not capture the creativity and originality of a person's work. I remind here again to Katalin Kariko and her fate as a scientist. She failed in that system. Our concept of universities should be that they can remain places where we can and must deal with issues that will only prove relevant decades from now. The useless knowledge of basic research is the foundation for innovation, as the history of the therapeutic mRNA concept has demonstrated. Not plannable, and also without guarantee. Like Helmut Schwarz, I would wish that this fact would be more strongly internalized in society, in the media, in business and politics. How much of the justified profits of the BioNTech will be diverted in future to new research topics that generate useless knowledge? It would only be fair if all the winners were aware of this. The establishment of science-driven funds or foundations that support talented, hungry young people willing to take risks, unburdened by metrics hamster wheels. That would be a good start. I would like at the end to point out that it is far from my intention to discredit research that is bound up with the utilitarian and ask, how can I solve a problem or achieve a practical goal? I myself founded a tech company 25 years ago, together with the engineers from the Technical University of Clausthal. It was financed by venture capital, and it was located in Potsdam near Berlin. However, I strongly advocate the importance of a science that also asks why, that seeks knowledge and initially only wants to understand, and that is granted dead ends and uselessness. It is such an honor for me that I can stand here today. It is an honor for me to be a member of the Swedish institution here at SCAS that acts as a catalyst for creating knowledge on the basis of transdisciplinary personal interactions of scholars, right in the tradition of the Institute of Advanced Study at Princeton and Abraham Flexner. Tack alla här i salen. Tack så mycket, Kristina.